Hey guys, happy Monday. As promised, I have a video here for you with the notes on chapter 3.3 since I'm not there today. So please make sure you have your notebooks out and a graphing calculator and that you're taking notes on this section. The assignment for 3.3 will be due tomorrow for 3rd hour and Wednesday for 8th hour. Okay? And then feel free to pause along the way if you need to. But this is just a quick review of logarithms. Remember that logarithms are used to help us solve for the variable when it's in the exponent of an exponential function. So that's why we reviewed exponential functions on Friday. So logarithms allow us to undo exponentials, essentially to solve for that variable in the exponent. So one of the first things we'll have to do with logarithms is be able to write exponential expressions in logarithmic form. So here on this page I have the two different forms, exponential and logarithmic. And if your exponential form is a base raised to an exponent that equals some sort of value, you can rewrite that into logarithmic form. Of course, you need to have a log. The base of the log is the same as the base from the exponential of the value, and that equals the exponent. So a logarithm is always set equal to the exponent because, again, the whole purpose of a logarithm is to solve for a variable when it's located in an exponent. So just remember that in logarithmic form, the log is always set equal to the exponent. Okay. So our first example here says write each equation in exponential form. So a log base 3 of 9 equals 2. So for exponential form, we need to start with a base. So the base is the same as the base from the log, raised to an exponent. So remember from logarithmic form, that's what you set equal to, and equals the value 9. Now mathematically we should check to see, does this make sense? Is 3 squared equal to 9? Yes. Okay. In B we have log base 10 of 1/1000th equals -3. So the base is 10, exponent is -3, equals 1/1000th, and is that true? Yes, because a negative exponent flips your base, so that would flip the base to be 1 over 10 cubed. 10 cubed is 1,000. Okay, last but not least, log base 6 of 1 equals 0. Base is 6, exponent is 0, equals 1. 6 to the 0 power equals 1. Yes, that's true. Anything to the 0 power is 1. Okay? Now, skill practice 2, this is going the other way. You take the exponential and write it in logarithmic. So, well, first thing we need to write something in logarithmic is the log. The base of the log is the same as the base from the exponential. So here the base is 2 of 32 equals, and remember a logarithm is always set equal to the exponent, so equals 5. Because the whole goal is we won't have that equals 5 there. We'll have log base 2 of 32, and the question will be 2 to what power is 32? Well, to the 5th power. And that's what we use the log to solve. Okay, B, log base there is 10 of 10,000 equals 4. And in C, log base is 1/8 of 64 equals exponent -2. Okay? So that's rewriting between exponential and logarithmic form. Now evaluating, again, remember the whole point of a logarithm is to solve for the exponent. So when we have something like log base 4 of 16, what you're really doing, if you think about this in exponential form, is thinking, like let's say we put equals question mark. We're asking ourselves 4 to what power equals 16? That's the exponential form. Well, these ones should be easy enough to do in your head. 4 to what power is 16? The answer is 2. So that means log base 4 of 16 is 2. Okay, here this is going to be 2 to what power is 8? The third power. And the last one is going to be 1/2 to what power is 8? Well, I know that 2 to the third power is 8, but this is 1 over 2, so that must be the negative third power because that would flip the base. Okay? Some more evaluating here. 5 to what power would be 125? That's the third power. 5 times 5 times 5. 3 to what power would be 81? I believe it's the fourth power. If you use a calculator, 3. So the third is 27 times another 3 is 81. Yeah. All right, and then 4 to what power is 164? Well, we have a fraction here, so it's most likely going to be a negative exponent. So the negative exponent would flip that to be 64. 4 to what power is 64? The fourth power. Oh no, 4 to the third power. My bad. So negative 3. Okay? So that's evaluating simple ones without a calculator yet. Now there are 2 special types of logarithms. There's a common log and a natural log. Those are the 2 buttons that are located on your graphing calculators. So the common log is a logarithm whose base is 10. And a natural log, we actually use ln, logarithmus naturalis. It's like the little Latin form of it. And I'm going to just use an uppercase n so that you guys don't get confused. So a natural log, we use a different notation. Instead of the log notation, we use ln. And the base is e, the natural base. So remember we looked at e on Friday when we were reviewing exponentials. It's the natural base. So the natural log has a base of e. Okay? So when we see these 2 written without bases, if you see a log written without a base and natural log, you won't see them write the base. You can assume for a common log that the base is 10, a natural log, the base is e. And that's what your calculator assumes when you see the buttons. Speaking of which, let me show you here real quick. Oops, get out of this. The log button is located, and the natural log button are located over here on the left. So here's log and natural log. So those assume base 10 and base e, and we'll be using those in a minute. Okay? All right, so this one says evaluate. We're going to first do this without our calculator. So the first one says log of 10 million. So no base listed here, so we assume the base is 10. So this is essentially saying 10 to what power is 10 million? Well, it's got 3, 6, 7 zeros, right? So 10 to the 7th power. Here, this would be log of base 10. I'm putting this in exponential form. 10 to what power is 0.1 is 1/10, right? That's how you say that number. So 10 to what power is 1/10? Well, 10 to the first power is 10, so 10 to the negative first power is 1/10. Over here, this is a natural log, so the base is e. So e to what power is e to the 5th? Well, that should be easy enough to see. To the 5th power. And then here again is natural logs. The base is e, so e to what power is e? The first power. So those are just pretty simple, common sense ones. Okay? Here we have some approximating, so you're going to actually just use your calculator to approximate to 4 decimal places. I will do 2 of them with you since these get kind of redundant, and you can do the rest on your own. So log of 229, I'll go to my calculator and I'll type in log of 229, close my parentheses. So again, this is a common log, so the base is 10. So this is essentially asking 10 to what power is 229. So we get 2.359835, blah, blah, blah. And so it said round to the 4 decimal places. So that would be 2.3598. After the 8 comes a 3, so the 8 stays an 8. 2.3598. And then I'm going to do D with you because that's a natural log. So natural log of 87. We push the natural log button here. It's underneath the log button of 87. So this is e to what power is 87. We get 4.659. 4.4659. Okay, cool. All right, these are just some quick simplifying ones. We should be able to do these without a calculator. So A is saying log base 13 of 13. So again, this is saying 13 to what power is 13? The base is 13. 13 to what power is 13? Answer is 1. B, natural log of E. Now the base of natural log is E. So this is saying E to what power is E? 1. A is saying A to the log base A of 3. So this is a log within an exponential. Exponentials and logs cancel each other out. So an exponential base A and a log base A cancel each other out, and we just get 3. Same thing with D. This is a natural log. This is an exponential with a natural base. And the natural log, which has the natural base. So those cancel each other out. We just get 6. For E, we have log base pi of 1. So the base is pi. Pi to what power is 1? Well, the power 0 is what yields a 1, right? Anything to the power of 0 is 1. F log of 1. It's a common log because there's no base shown, so we assume it's 10. So this is 10 to what power is 1? Yep, 0 again. Here we have in G log base 9 of 9 to the power of root 2. Well, that's a 9 to what power is 9 to the root 2 power? The root 2. In H, log base 10 of 10 to the E. That's another common log since we don't see the base written. So that's saying 10 to what power is 10 to the E power? Must be E. Okay. All right. The last little part here then is graphing logarithmic functions. Now, like we said, logarithmic functions are the inverse of exponential functions. And we talked about inverse functions last week, Thursday. They undo each other. So if we remember the key features of logarithmic or exponential functions, right? They're curves, they have horizontal asymptotes, the domain is negative infinity to infinity, the range is restricted by where the asymptote is. The logarithmic graphs are the inverse of that. It's still a curve, but this time it's got a vertical asymptote, which is affected then by the horizontal transformations. Your range is negative infinity to infinity, but your domain is restricted by where the vertical asymptote is. So this table here, oops, yeah, we'll go back to that problem. This table here kind of lays out the differences between exponentials and logarithmic functions with respect to their graphs. So the domain and the range, the asymptotes, horizontal for exponential, vertical for logarithmic. And then we know how to tell if it's a growth of decay for exponential. It's similar for logarithmic. So if you want, you can take a minute to pause the video and copy down some of this important information. But a lot of the graphing we do with logarithmics is just going to be utilizing our graphing calculator. Okay, so if I back up to this page, it says graph the functions. We have y equals log base 4 of x. Now, one thing that I want to say is when we go to graph this, in our calculators, we have to be able to enter logs with different bases. Because again, the log button on our calculator assumes base 10. So our calculator doesn't have that. It's a log base 10 button. So if we have something like log base 4 of x, how do you enter that? Well, the newer graphing calculators have a button that allows you to change the base. It is located in kind of two different areas. If you go to math and arrow over to the number panel, I believe down all the way at the bottom, we should find something that says log base. Oh, maybe not. Is it on the number panel? It's in here somewhere. I should have looked ahead of time. There it is. Okay, it's on the number panel. So if you see this log base option, this actually opens up a logarithmic with an editable base. That's kind of a cumbersome process. So the newer TI-84s have a shortcut panel. If you push alpha, window, it opens up a shortcut panel of the most commonly used functions on the calculator. Log base is number 5. So hopefully most of your calculators have this. Now, if your calculator does not have either of these, or you're using like a scientific calculator, then you can still calculate a logarithm or type in logarithms that don't have a base 10 or a base e using what's called the change of base formula. And this is something that we'll look at again on Wednesday, or Tuesday and Wednesday. But just for graphing purposes, if you need to, well, I guess you wouldn't be graphing anything on a scientific calculator. But if you're using a graphing calculator that doesn't have the change of base option. So like, let's say we have a log base b of some value a. We want to put that in our calculator where the base b is not 10, so it's not a common log. In order to do that, you would take the log of the value divided by log of the base. So like if we wanted to graph in a minute here log base 4 of x, you would have to type it in as log of x divided by log of 4. Or, again, just use the change of base button on your calculator. Okay, so let's do this one, log base 4 of x. I'm going to go to my calculator. Y equals, clear out anything that's in there. And I'm going to go alpha, window, and it's number 5. And it was log base 4 of x. And then we go graph. And so we got a couple interesting things happening here. It is a curve. The vertical asymptote is the y-axis, so x equals 0. And what we notice happening here is that the calculator shows it appears to stop, but it really isn't stopping. It's just getting really close to the asymptote, in our calculator with the limited screen size and pixels can't show that. So it actually will continue all the way down following the vertical asymptote there. So when I go here, I can also go second graph to get a table of values. I see I have like 1, 0, 4, 1 that I can put on my graph here. And I know that this is my vertical asymptote. So just make a nice smooth curve. Okay. You can see here the domain then. It's not asking, but just in case it did, would be 0 to infinity, 0 exclusive since it's an asymptote, and the range is negative infinity to infinity. Now, in B, we have log base 1/2. So I'm just going to quickly switch here in my y equals. It's going to be log base, oops, we need to change a base button, so alpha window, option 5. Log base 1/2, you can either do 1 divided by 2 or 0.5 of x. Graph it. Similar setup, the y-axis, or x equals 0, is still the vertical asymptote, but this time the curve looks like it's almost flipped or inverted. We'll talk about why that is in just a second. But if I go second graph and get the table, again, I've got the 0.10 and 8, -3 look like two nice graphable points. Now, the reason why this curve almost appears to be inverted or flipped is because it has to do with the base. Now remember, exponentials are the inverse of exponentials, or excuse me, logarithms are the inverse of exponentials. So if our base of what would be the exponential in A is 4, that would be a growth function. And our base of what would be the exponential in B is 1/2, that would be a decay function. So it would follow that for logarithmic graphs, a base 4 would appear to grow, increase, and a base 1/2 would make the logarithm decrease, because 1/2 is less than 1. Okay, cool. Let's try some more. Here we're going to look at some transformations. So we have shifting left or right, opposite h, keep the k, and then reflection or vertical stretch or shrink shown by a coefficient. Now, what I do want to remind you of is that a vertical asymptote changes based on the horizontal shift this time. Because a vertical line can't move up or down. It already goes to infinity in both directions, but a vertical line can shift left or right. So we're going to be looking at that opposite h piece to tell us where the vertical asymptote goes. So in this example, we have log base 3 of x minus 4 plus 1. So the horizontal shift, this moves left 3. Oh, excuse me, I totally messed up. I don't even know what I'm looking at. This moves right 4, up 1. The right 4 is what moves the vertical asymptote to x equals 4. Now, I'm going to go ahead and put this into my calculator to get some values. So log base 3 of x minus 4 plus 1. And we're going to need to use that change base button. So alpha window 5, log base 3 of x minus 4, and it was plus 1. So let's graph. And we can see the shift there. And again, the base here is 3, which is more than 1. So this should appear to be a growth style function. So if I go second graph, I can get some points, 5, 1, 7, 2. Looks to be nice. Follow your asymptote, put arrows on the ends of your graph. Okay. Identifying domain, easiest way to do that is just to graph it and look at where your vertical asymptotes are. So this one says write the domain log base 2 of 2x plus 4. All right, let's take a look at the graph of that. So y equals, change your base button, alpha window 5, log base 2 of 2x plus 4. Let me make sure I got that right. Yeah. Okay. So when I graph that, it appears that there is a vertical asymptote at x equals -2. So that means the domain will be everything from -2 to infinity, -2 excluded. Which makes sense, because if you remember from our transformation unit, you would have to factor out that 2, and then you get x plus 2. And that's your horizontal shift right there. Opposite h means left 2. All right, natural log of 5 minus x. Some of you should probably be able to predict what this will be without even graphing it. I get 5 minus x. We have a reflection here due to that negative on the x, reflection over the y-axis, and then we also have a shift, what appears to be right 5 units. So this time our domain is going to be everything from -infinity to 5, of course exclusive. And then last but not least, we have log of x squared minus 9. Oops, gotta go back to y equals. This one's interesting because it's got an x squared, so that means it's going to have 2 branches to the logarithm, which also means 2 vertical asymptotes. And then we'll have to write this in interval notation to represent the 2 intervals of where this function is. So it's got the 2 asymptotes at -3 and +3, and there's no graph in between the 2 asymptotes. So the domain will be -infinity to -3 and 3 to infinity. Oops. Just like that. Okay. All right, cool. Here's your guys' assignment. I've taken off those last 4 at the bottom there. Use whatever time is left in class today to get started on that, and then that will be due tomorrow or Wednesday for 8th hour. I will also be checking your 3.2 assignments on the block day, and we'll go over any questions you have from that stuff. Feel free to email me if you guys have any questions. Otherwise, have a great rest of your Monday, and I will see you tomorrow.